So, hello and welcome. Woohoo! Let's make a sound check first. Can you hear me? Is this like, am I audible? It's also a chat test. Let's see, can got this deep. All right. Okay. Nice. Okay, everybody can hear me. So we got 1 more minute. Let me already write the topic on the blackboard. Whiteboard. Yeah, this is a whiteboard, right? I hope this doesn't break. Today's topic is functions. So, 1600. Way. Okay, hello and welcome to the live stream. Okay, yeah, today's topic is functions. And functions are actually like a pretty cool concept in computer science because they describe essentially the entirety of our work, right? So, I mean, what we do as computer scientists is pretty often, just we have, so someone comes to us and says, okay, I have, some problem, right? So I don't know, in this problem, we have a set of instances, right? And what we want to do is we want to build, some kind of block where, all the problem instances can come in, and out come the solutions. Yeah, so essentially pretty easy concept. We got a thing where something comes in and something gets out. That's the whole magic. So yeah, so we're interested today in this black box and how we do it. And as this is like modeling, how we can transform things from A to B. And the thing is, we had in the lecture already a tool to model this. So as of now, we know sets already, and yeah, so we know the function f to be from the set A to the set B, and what such a function is nothing else than a subset of the Cartesian product of A and B, which is a relation, right? So let me quickly cross down. So the Cartesian product of A cross B is just if we have. So let's make an example for this one. So if we have a set X, which is 1 and 2, and a set Y, which is 3 and 4, then the set X, the Cartesian product of X and Y is the set of all tuples. So all combinations that we can make from here, right? So we have 1 and 3, 1 and 4, 2 and 3, and 2 and 4. And that's the important thing. So a function is nothing else than a set of tuples, but a specific set of tuples. So we know that like an arbitrary set of tuples is just called a relation. So where we say, which thing gets where, but we want to constrain functions a little more. So we say for all such that, for all, let's say, lowercase a in A, there is there is a B in B, such that let me just write this: f of A equals B. So yeah, let me say this notion. So as we have, this concept of, something goes in, something goes out, we have the f of A just means if we put the A into the function, the B is the value that comes out. And yeah, what we have in this function is that all our input values are mapped somewhere. So there's no value that goes into some kind of void or something. So the special thing about functions is that everything that goes out kind of comes out somehow. I don't know how, but like, yeah. There's this cool thing from Portal: speedy thing goes in, speedy thing goes out. It's not the same concept here, but yeah, you get the thing. Okay. In this beautiful sentence, use a lot of stuff like, for all there is, and so on and so forth. And this is why I call this tutorial like as a connection of functions to predicate logic, because we can use predicate logic to define functions. And yeah, so let's do that, because it's just, looks nicer and the mathematician's soul kind of gets into it. And also, computers can understand it, which is often a very good reason to do something, because that means that in the future we might not have to do that on our own. Sadly, not quite there yet. Okay, so how do we phrase this in first order logic? It's not entirely phraseable in first order logic, but let's get as close as we can. All right. So we say, first of all, for all. So the first thing that we need as a connection is the predicates that we've seen before are essentially sets. So the first important thing is predicates are essentially sets, right? So if we have, so essentially we have our A, and what I just wrote, this, or use a small a. So small a is in A. Essentially just means, there A such that A of A holds. Yeah, what I mean. Yeah, let me use this symbol. So yeah, so a predicate for its arguments just defines, which of these arguments are in their set and which aren't. Right? So this is what we're going to use to model the functions. And yeah, so a function obviously is a predicate that takes two arguments, right? Because we have a set of tuples here, or a subset of these tuples. So we say for all A, such that A is an A, implies that there is a B such that B is in B, and I will use a big F for this one, and F of A and B. So let's use uppercase F as the predicate for F. Okay, so this is the first condition that needs to hold. I should use now it's a little nicer. Yeah. Okay, so we say, okay, each element in here has an element that's in here. The other important thing is that this element must, so it is not only that it maps to some element, but it maps to only exactly one element. So, this is just basically saying, okay, each A is present, but we need to have a second condition. And for that, we need to extend our predicate order, our predicate logic a little. Let me just show how it looks like. So we also state that for all input values, so if an input is an A, that means that for all X and Y, let me just phrase it where we want to go. So we not only want to say, okay, we match to anyone, but we match to only exactly one, right? So like we cannot. So we assume that like every of our solution, that there's only one solution, right? Yeah. So we say that for X or for Y, if our function and the value A maps to X and the value maps to Y, yeah. So if both of this is happening, then there must only be one can do this, and this is if X is equal to Y. Can you see that? Yeah, perfect. Yeah, this looks weird. So what we're essentially stating here, okay, if we are mapping to two values, the value must be the same. So this is just stating, okay, like if we are already mapping to some value, there must just not be another value. So like if we're matching to two different values here that are not the same value, then this clause would be insufficient. So would be heard, right? So in fact, these two parts can be stated in one statement that I think might have been introduced in lecture. I don't know. Let me introduce it for you. I need space. So yeah, let me remove everything that's human readable. So these together are often written as for all input values, so for all things that are input values, we say there exists exactly one, and we write this with like this exclamation mark, there exists exactly one B such that B is in our output and and f of a b. So these two bad boys. Okay. Yeah. So let's let that sink in. I would just quickly remove that example so we can read it better. The important part when teaching functions is that we have to remember for quite some time that everything that we do is essentially only giving us more tools to express something. So when I started computer science, I was asked, what do we need these relations for, or what do we need functions for? And I was like, we need them for quite a lot of things, but as of now, they are like tools. So, actual machines in the real world, they do something. So technically, we don't need to think about when what like a function is, or like which input into the machine comes, like produces with which output. But if we want to understand the machine, we have to find a mean how to talk about the machine. So this is why we have functions as a thing of like we describe something goes in, something goes out, and we have first order logic as something to even describe it in a machine language, kind of how this something goes in, something comes out looks like. Okay, breaks over. Let me remove this part. So now we have just defined, what a function is. Gotta maybe speed up a little. I want to give some quick examples of things that are not functions, which is important to understand all this. Maybe one question to the people who are currently in the chat. Please write whether you want to today stress more on function composition, what we had in the quiz last week, or whether you want to stress more on injection, surjection, and bijection, which will be relevant for tomorrow. So please write that in the chat while I do some magic over here, and then I will adjust the tutorial. Okay, this is the first order thing that if we say, okay, we model this function by the predicate f, oops, missing a bracket here, then what this predicate has to fulfill. Things that are not functions, not functions. To circle. So it's in teaching, it's bad practice to say if something is not something, but like so you should rather say what is something. But like I think these examples are quite good to understand. So let's say g is a function. Maybe we even let's use so let's use just some so I say like from the set 0 and 1 to the set 0 of 1, that's totally sufficient to tell you what's not a function. So first example, the d of let's do it that is g of 1 equals g of 0 equals 1. We can write that, and so yeah, this is how we define for concrete values how they look like. Sometimes there's a different symbol used here, but we use equivalence for today. If we stop now, this is not a function. Let me show you how the graph of this function looks like. So the graph of g, there's only one tuple in there, which is 0 and 1. But we said that all input values have to have something to be mapped to, and so this is not a function because all a needs something. So the 1 is not mapped to anything, so this is not a function. Okay, I need okay. Let's say h again from 0 1 to 0, 1. Yeah. Oops, this is supposed to be an H. Okay, and we state something like this. H of 0 equals 1 and H of 0 equals 0. Yeah. This is already, so we're, mapping the same value to different others, right? In the graph, it looks even more even weirder. So we essentially have a set of 0, 1 and 0, 0. Yeah, which obviously hurts the condition here that the output should be only 1. Yeah, so for each input only 1 output. For this example, there, however, sometimes we want to model that we map onto several things. And there's a solution to that one. It's obviously not defining it by like this, but oops. But if we want to define this, then we can say, okay, our function doesn't map from 0, 1 to 0, 1, but into the potency, the power set of 0, 1. Power set always has a very freaky letter. I can never write this one. So if we now map into the power set of 0 and 1, we can let H map into, a subset of what we have here. So if you want to actually model this stuff, this would now look like this. So we map H of 0, for example, to 0 and 1. So the subset 0, 0 and 1. And maybe H of 1 to, only 1. Yeah. Now correct. Yeah. So that's a good thing because sets can also be treated as elements, and we can have sets of sets, right? So if we actually want to model that, a function maps into several things, we usually let it map into the power set, and then you can write something like this, right? So that it maps to several elements. Okay, this is just a funny trick. Yeah, let me go over there and remove some stuff, and then we will go to the next topic. Hope I'm not in the way. Okay, so I hope we all remember, what functions are. Every input value has exactly one output value. This is, by the way, pretty much the only constraint that functions have. I think we don't need that currently. So these sets over here can obviously also be infinite, right? So you can also make mappings from the natural numbers to natural numbers. So the principle works exactly the same. Yeah, only that we can't write the whole function down. That's the whole difference. Okay, let's look at the chat. Injection, okay. So injection, surjection, and bijection. All of these are properties of functions. And so our overwhelming law, again, of the D, let F be predicates cut, oops, for the function F from A to B with a and B having predicates with the same name. Predicates with the same name. Okay, so for all our input values, we state that there is only one output value, D, B, and F, and B. So this is the law that holds for all functions. All functions. Now, sometimes certain things are interesting. For example, when we have a coding function, the decoding function C that goes like to, so we have a binary representation of a string of length n, right? The D to so this is a typical coding function. So we have some strings of bits, right? And you want to encode this into other strings of bits. And now it's interesting because sometimes we want to reverse that coding, right? So if we, for example, compress something, after the compression, we kind of want to get the original object again, right? And this is what we have our first thing for, and that is coding functions are always at least injective. So injection, informally, means no object in B is hit twice. Yeah, because why is that important? If two different objects in C, in you know the first vector hit the same object in the output, then we can't reverse it. So let's say we have like only the X, Y, Z. So let's say we have only 3 objects that we kind of want to encode, right? If we, let's say we have only, or let's say we have 3 possibilities to encode those, right? So to, I don't know, star, circle, and everything works fine if we, you know, map, for example, X to the circle, Y to the star, and Z to the plus or something. Because now, if, you know, someone gives us the plus, we can just, you know, follow back these arrows and land at our Z, for example. Right? We get the circle and we land back at our X. What would be really inconvenient is if we would do it like this. So, for example, the X maps to the star, the Y maps to the star, wherever that maps, right? So for Z, we are fine because, yeah, if we're getting a plus, we know, okay, it could have been only Z. If we're getting a star, then we're fucked because, like, a star maps to X or Y, and we don't really know what was the original object, right? So that's why encoding functions are always at least injective. So okay, let's phrase this with our cool predicate logic. So we have this up in these formulations here. Remove that one. That's a cool thing with a live stream. I can pretty much freely remove stuff from the whiteboard. And if that was too fast for you, just pause the live stream. I kind of like that. By the way, if something goes too fast for you in general, or you need extra explanation, please just write it in the chat and I'll read it. Hopefully. Yeah. So please use the possibility of the chat. So the 9 people currently watching, you have the privilege on this live stream. Okay. So injection. We have time. That's good. So for injection, we say again for everything that's an input. Oh wait, sorry. No, we don't. So injection is essentially about the output. So we say an output should only be hit once, right? So we had, this. Shouldn't have removed it. So if we have, X or Y, right? We want to avoid that, our star is hit twice, right? So each output object should only be hit once, right? So so this is about the output values. Yeah. So for on B, if something is an output value, we state that there is only exactly one input. Yeah. So that this is an input, and we map to that input. F of A and B. Yeah. And brackets. Yeah. Like this. So if that is the case, the function is injective. There's a question. X1 and 2. Okay, so there's a question. So short intermezzo. So the question is, first of all, the D. Your syntax for the function is a little off to the syntax we usually use. So I will write this the way that I hope I understand this. So you're given a function f 0 infinite into r. I'm not too sure what that. So the thing is, at first you're writing a tuple, but you need a set. So I assume you just mean the set from 0 to the natural numbers together with infinity. I hope. So here needs to be a set, not a tuple. And you map this into the real numbers, probably. And f of x equals, x plus 1 plus ln of x plus 1 plus ln of x. And we see, okay, now we say that let g of x, let g be the inverse of f. The inverse, first of all, only works if the function is at least injective, and if we cut some values here. But so the inverse is exactly what we want to do in the encoding stuff. So we wanted to trace the errors back. So our f of x maps to some weird values, and now g should be like the exact reverse. Well, essentially, if you now want to have the concrete value for g of 2 or something, you have to find the number in R, you have to find the number in n together with infinity that maps to the 2 in R, right? So this function kind of maps somewhere into R, and you just take 2 as the number of R. And what you are stating here is just, I hope you can still see that, should be fine. The question is, which value of x plus 1 plus ln of x equals 2? Yeah. So this is how you formulate the question. Yeah. Because these are the values that we map into the real numbers, and now you gotta transform this until you actually know the value of x, and then you know which value mapped into the 2 of the real numbers. Okay. So if you want to say only the positive real numbers, it's usually written as R plus. Yeah, you can do that. Into here we have all the real numbers. It doesn't really matter for the functional sense. So if you take the inverse and then want to get like the actual value of the inverse, you have to know which of the inputs maps to your output. In mathematics, we often write this like this. So this is where our inputs point in. They have to be 2, and then you reposition this such that somewhere in the end it says x equals and whatever x equals 2. Okay. The reforming, please just do that on your own. But like this is the principle of how we would be doing this. Okay. Thank you for the question. Okay, getting back to injection. So so we formulated injection. So for every output value, there is only exactly one input value, right? However, now we can have another problem that would also be kind of annoying for our that would also be kind of annoying for our compression problem, and that would be, for example, if you have some kind of overfitting, right? So if you have like only 2 inputs, so only 2 input values, but like I don't even name them, it's too many, right? So too many output values. So if we do something like, let's do red. If you do something like this, right? That is super nice. Maybe name them 1, 2, 3, 4. That's super nice because at least we're not hitting anything twice. But we can also know if we reverse that one, there are certain values that just don't map towards anything, which is kind of annoying, right? So in the reverse, they're just things that we have no use for. So what we now want to state is that each of these elements is hit at least once. So which of these elements is hit at least once? So for 4 elements, obviously this can only work if we either remove 2 from the outside or put 2 extra ones in the input, z and I'm out of letters, omega, whatever. Now hit our output values. An important thing that can happen if something is only surjective is if we have less output values. So, for example, we cut this one. For sole surjectiveness, we are totally allowed to map an element twice. This looks really crappy. But yeah, you get the point. So, you know, this element here is mapped once and twice. Yeah. Let me get for an example for this one. Yeah. So, for example, such a setting is interesting if you want to. So let's say like these things are working desks and you want to assign jobs. This is pretty often the case that, like, you know, you have some, I don't know, mail fault or something where people write stuff that a company should do, right? And every job should at least have someone working on it so that, you know, you finish at the end of the day, right? And then you would say, okay, this has to be at least surjective. So each job is done by someone. And if more people do the same job, yeah, you just don't care. Okay, let me quickly look at the questions. Let's see. Okay, yeah, okay, you seem to have figured it out. So, okay, so let's model this surjectiveness as the same predicate order function. Okay, let me remove the example here. I need space here. I'm really bad at managing space, but that's all right. At least my whiteboard space. I'm completely crushing this example now, but that's all right. Yeah. So, surjection. Action. We now talk about yeah. So essentially, we talk about output values. So for each of the output values, yeah, BFB implies that there just exists an A from the inputs that is mapped towards. Wait, have I done an error? This looks really weird. Injection. Oh, sorry. I did an error in injection. Sorry. Good God. This is embarrassing. Okay, so you see what I'm starting with. So, of course, in surjection, we're mapping to outputs, and we say, like, you know, each output has to have some input value that is being mapped to. In injection, that doesn't have to be the case. So in injection, we can have, you know, some value that just no one maps to. So, you know, if we have something like this, this is perfectly fine injective, but this output value doesn't have anything that is being mapped to. So we got to embarrassing. Please write in the chat how I can make these cool thumbnails on the videos so that that the people watching that afterward can see that there's an error. All right, so let me first phrase it how I would phrase it by intuition, and then we maybe make it nice. So essentially what injection says, if we have two input values, so for all A and for all B, if they both map to the same value, which is what we want to avoid, f of AB and f of, oops, not AB. Wait, forgot the types also. So wait, for input values and output values for Z. So if yeah, A and B, let's call it maybe A and A prime. We have the A's together. So A and A prime. If these are from the inputs and Z has to be from the output, A and A prime and B, Z. We should also use the B. Okay, so if you know the first ones are from the inputs, the second one is from the output, then this is getting ridiculously long. If A maps to B and A prime also maps to B, and I don't have space anymore, then this has to imply that these two are the same. So A equals A prime. Because yeah, we want to avoid that two things are so two different values are hitting the same spot. All right. Okay, this looks horrible. Let's phrase this a little more readable. How would we do that? No, there's no. I can't see immediately like a nicer way to do it, but so we can't use the exactly one because why can't we? Let me rephrase this one. Sorry, this is the problem with live stuff. I have no script to do this one. So yeah, former version was correct, but it just looked horrible. So we state that now I know. There's a trick. We forgot something. So put values B of B. And now we not only state that it is an output value, but we state that it is a value that is being hit in the first place, right? Because if something is being hit, it should be unique, but if something is not being hit, we just don't care, right? So we not only state this is an input value, but we also state that there exists something. Okay, yeah. So okay, we first say okay, it's an input, it's an output value, right? And then we say if there exists an A such that we hit that B, that means that the same B pardon, that that there has to be only one A where this hits. So okay, let's write it like this. Yeah, okay. No, we can do this. So if it's an input value and it's being hit, right? So there is some A such that, we hit A and B. Then, now this makes more sense. Input value, we are being hit. Then we say we are only being hit exactly once. So we now state there is exactly one, let's call it A prime. We could technically also call it A because this is another binding, but I don't want to confuse it. So there's some A1 A prime that we are being hit by. A prime of B, right? That makes a whole lot more sense now. Let me do the brackets correctly. Here we go. Okay, now we paired it. Sorry for that one. Okay, so if we be so for each input value that is being hit, so for which there is some value that is being hit, it follows that there's only one value that's being hit. And yeah, surjection is a little easier. So if we are an output value, then we are hit at least once. So there is at least one A that we're being hit by. That's correct. Remove this one. So, and the interesting thing is now, what happens if we put these two together? So if a function is injective and bijective, and let's look at this example. So this function is injective because we don't hit anything twice, but it's not surjective because there is something that we just don't hit, right? However, if we kind of want to make it surjective now, so make something like this, right? This doesn't work because then it wouldn't be a function, right? So because this value would then point to two things, right? And the same thing here. So if we I cannot make it surjective because we have too many outputs. It just doesn't fit that we assign of these ones only one in here. Right? Also, the other case, if we have too many inputs, like this one, x, y, z, right? Now this function is perfectly surjective, but not injective anymore, right? So this doesn't fit. So if we now want to combine those two things, it only ever works if the input and the output set have the same size, and then we call it bijective, right? So bijective is injective and surjective. Yeah. This is now a very bijective functions are very neat. Going back to our encoding example, this is when we can completely reverse what we're doing, right? So we encode something to some value, and then we can always retrieve it back. So bijective functions, they always can be reversed. So we saw that in the question. So if you're having some reverse function, this only ever works neatly on a bijective function. I mean, technically all injective functions have these reverse functions, but then you have to cut a bit of the output space. So when the range is too small, when the range is too big, and you reverse it, has a smaller domain than the range if it's only injective, but not surjective. Okay, but yeah, if it's both, it's pretty cool. So we have a one-to-one mapping. Certain things follow from this. So the two sets are the same. Actually, let me give you some human language examples of what we can say from injection. So And let's go over to human language, a segment that we call human language. So, let's start with injective. Yeah. Injection only works if the output set is at least as big as the input set. Don't take this out of context. So if an injection works, we know that the set where we map into has to have enough elements to fit what we put in there, right? So for example, here with 2 elements it works. With a third one, it wouldn't work anymore. If we had only 1 element, it would also wouldn't. If we had 1 element less, then this wouldn't work anymore. So then this couldn't be injective anymore. So then the output set has to be at least as big as the input set. You can probably now imagine that for surjection, another thing holds. So surjection only works by the way, these are if and only ifs. So EFF is like if and only if. So surjection only works if and only if the input set. There's 2 ways to phrase it. Either we can say, the input set has to be at least as big as the output set. So if we don't have enough inputs, like we would in here, then the inputs wouldn't fit in the outputs. Or as I will now phrase it, so it looks a little more similar, but the statements are equivalent. So surjection only works if and only if the output set is at most as big as the input set. Right? So we have here injection for the output is at least that big. The surjection is the opposite. And now obviously for bijective, for bijection, it follows, if it's at least and at most that big at the same time, it has to have exactly the same size. So for example, you can describe cardinalities of set with injection and surjection, and if you have a bijection between 2 sets, they have the same cardinality. So this also works for infinite sets. So if you have, for example, try to map the natural numbers in the rational numbers, you will find that there is a bijective function. So these 2 sets have the same cardinality, have the same size. Whilst if you try to map the natural numbers into the rational numbers, this will not work. There's no bijective function. There's a nice proof about this one, but we won't do that today. So this is to give you like a feeling for injection and surjection. But so it's important to keep in mind, especially the human formulations of this one. So injection, each element is being hit at most once. Surjection, each element is being hit at least once. As examples, you will probably get the graphs of a function or a function, but like you can draw the graphs if you want. And then you have to determine that for the function, yeah, if they are injective, surjective, or maybe bijective. Yeah? And maybe let's, for the last few minutes, do a few examples of this, again with like with a function over finite things. Examples. So we have the functions G1 and G3, right? They again map from 0, 1 to 0, 1. And now, yeah, so let's say G1, G1 of 0 is equal, this is now fairly boring, but that's all right. Okay, so G of 0 is equal to 1, G1 of 1 is equal to 0. Yeah, this one is obviously injective because you can see it here. No output value is hit twice. So also if we write the graph of G, you can, if you want, write it neatly under each other, then you can check it easier. So yeah, 0 maps to 1 and 1 maps to 0. Yeah. So yeah, you can see, in this part that no element is being hit twice. So that makes it injective. Maybe we need more space. Yeah. So injective. Check. What about surjective? Yeah, so surjective means each element is hit at least once. We also have that. Yeah, so we have hit a 1, we have hit a 0. So each element in the output is being hit once. Yeah, and as we have both of those, it follows that the function is bijective. All right. Let's go with another example. This is getting quite crowded here. G2 of 0 maps to 0. G2 of 1 maps to 0 as well. Yeah. This is yeah. This is wait a second. Sometimes confuse these things. So it's one but not the other. Let me do it. I also need to break it. Mm-hmm. So definitely a function. Let's check. Is it injective? Yeah. So yeah. Each value that is being hit, that was the note in my head. So each value that is being hit for injective must not be hit by two targets. So most ones, that is not the case, because the 0 is being hit twice. So as injective states that inputs must be hit at most once, this is not injective. What about surjective? yeah, surjective is fine because no, it isn't. Wait, what am I telling you? It's late. It's getting late. It's not injective. It is. Not surjective. Oh, yeah. Sorry. It's also not surjective because yeah, it's not injective because we have an element that's being hit twice. So if we reverse that, we don't know where to put the 0 to. Yeah, it's also not surjective. Yeah, now got it. It's not surjective because there's an element, meaning the 1, that we haven't hit. So the ones are unhappy. So this is neither injective nor surjective, and then obviously not bijective. Right? All right, doesn't work. So for a third example now, okay, in my head, I now want to obviously generate examples for something. Pardon? Wait, let me check the chat. So if you have injection and surjection at the same time, then the cardinalities of the set are equal. However, if you have only one and not the other, then you only know something about the sizes of the set. Okay, let me come up with. So the problem is these two sets have the same size. I'm pretty sure there are like statements about that because I now want to so let's have a thought example. I actually wanted to create an example where we have a function that is not injective but surjective. That doesn't work because let's try making something that's not injective. So an element is being hit twice. So we want to have something that's not injective. But surjective. And if we have, for example, OG3, and okay, we have to hit something twice, right? So G of 0 maybe goes to 0, G of 3 to 1 goes to 0. Yeah, this is nice. It's not injective anymore. But to make it surjective, we now have to hit the 1 with something. Right? So yeah, for two sets of the same size, this doesn't work. There's just nothing that's like either ones or the other. So yeah, probably there's some proof that if the sets are equal, then there always is like a function is either bijective or neither. But I'm not 100% sure, so don't name me on this one. Wait, no, can't be. Sorry. Okay, so this is a special case. So for these two sets, it's either both injective or surjective or neither. But this is not the general case. Yeah. So for example, if you go to the natural numbers, I'm pretty sure I can make an example where that's not the case. I haven't proved that currently, but yeah, let's look at it. So this doesn't work. But what would work is if we would add, a third element to the inputs. Let's say a 2. This is supposed to be a 2. Then we can obviously state, G3 of 2 goes to 1, and then we're happy because we hit the 0, we hit the 1, so this thing is surjective but not injective. Can you see that? Yeah, you can. Cool. Okay, if you want to make this the other way around, so with is injective but not surjective. Again, with the setup that we currently have, this one doesn't work because our input set is bigger than our output set, and so we cannot have an injective function. We fix that by removing the 2 from here and just putting it into that set. So 2 the D. Yeah. So obviously we don't have a third entry here, so now we just map them wherever we want. So the 0 goes maybe just to the 0, and the 1 goes to the 2 or something, right? Now we're definitely being injective. Yeah, nothing is hit twice, but we're obviously also not surjective because we kind of missed the 1. We missed the 1. Yeah, so this would be an example for a function that's injective but not surjective. Yeah, there are a lot more properties when it comes to like bigger sets or even infinite sets or something, how injective and surjective behave. We will not go about this today because the time's over, but yeah, if you can think about it, maybe think about for which sizes like a function can be, a certain thing, either injective or surjective or neither or something. So yeah, as an example for your home, try coming up with functions that have bigger sets over here. That's injective but not surjective, or something that's only surjective but not injective. Yeah, exactly. So then let me check the last questions. Okay, so maybe one last example. So the function, in the chat you post the function f of x equals x squared. Yeah. Now x squared never gets negative. However, if we permit negative numbers in here, and we say this is a function from let's say f is a, why didn't this write? I need a new pen. Shit. Okay, my pen broke. So let's say f is a function from the reals into the reals. Yeah, we can define this function, and yeah, this one is neither injective nor surjective. So at least at first glance, let me think that through. Okay, so the first thing we notice is x squared never gets negative, right? So we are obviously not hitting a lot of reals, right? So all the negative reals, to be precise. And therefore we cannot be surjective, because surjective means we hit every element. Yeah. So this one is definitely not surjective. Yeah. Let's check for injective. Yeah. So injective, we say each element is being hit at most once, but if we put f of 1 and f of minus 1, they hit the same same element here. You can barely see that. Yeah, that's good. So 1 and -1 each map to 1. So there are two elements that map to the same element in R, meaning that this function is also not injective. Yeah. So this function is neither injective nor bijective, not surjective, and then obviously not bijective. All right. Please ask me more questions. Let's see. Can I swim this? No. Okay. Yeah. So if there are no more questions, then thank you everybody for joining. Yeah, it's pretty awesome, making some extra explanations. It's kind of sad that we don't have enough time to get through like the entirety of that stuff. Yeah, the whole problem with functions and having all this definition with injection surgery and so on. As I said in the beginning already, this is only like a mean how we describe something, and this is just a language that we're using to describe something concrete. So take these as tools. Take these as just things that you have in your reservoir to describe things. And if you then go out into actual computer science, and then you see certain properties like I have with that coding, right, or with the job assignment or something, what kind of function you need, and you can tell this to either your coworker or your computer or something like this. Okay, then in that sense, thank you very much for joining. Thank you all very much for joining, and this is for me. Bye bye. See ya.